So are you able to see my screen? Hello?
Yes.
Yep. Okay, good. Yeah, because I'll be unable to see you, and yeah, so just keep me if you have any questions, and or my writing is horrible or it's unclear, then just let me know. Okay, so welcome everyone. And today I'm going to speak about this work in progress called on Hennessy-Milner theorems for coalgebras. And it's also so there are no like final theorem as such here, but I'll just end. My main purpose was to give a brief introduction about these Hennessy-Milner theorems, and then say and give just a status or update where we are in this quest. It's a joint work with basically two teams from Germany. One is Barbara Koenig from the University of Duisburg-Essen, and her two PhD students, Sebastian Duke and Carla Messing, together with another team from Erlangen, headed by Liz Schroeder and Paul and Jonas Foster. Now, before I start all this, maybe I should say a bit about how we got into this. Previously, I was part of, so I was working with Barbara and her group, and recently in CSL Computer Science Logic, which was a workshop conference held in Warsaw this February, we published Hennessy-Milner like theorem for metric transition systems, and also for behavior equivalences which were not studied previously in the Van Klebeck spectrum. We gave an ordered theoretic approach, and so we wanted to generalize that paper to a more categorical setting. And in the meantime, Lutz and their team also were interested in tackling this problem, and they were coming from this graded logic approach. Even if you don't know about these things, so it's fine. It's just about where we are, where we wanted to go. And then we decided, okay, we should work together and see whether our general results can be translated into others' framework of Lutz and vice versa. But in today's talk, I'm not going to talk about that. Rather, I'm going to just give you a personal story of how I see this work is developing. So, just a second. And so the idea is I start off with the structure is quite simple. The structure is I start off with some basic introduction about this Hennessy-Milner theorem, or from the 80s. It gives some survey about the progress between 80s to 2010s and 2015 roughly. And then I start my categorification. So basically the categorification will have three dimensions. How do I model my systems? And then there is something called conformances. And lastly, behavior conformances. And with this, I'll be able to say what Hennessy-Milner theorem is at a higher generality. So moving back, so let me try to explain this this result from the late 80s, basically, which was first shown or was first proven by Matthew Hennessy and Robin Milner. But instead of going directly into the result, let's start off with some context. And to give you a context, so roughly around 80s, um, Robin Milner and Tony Hoare, they were interested in designing what is now these days called process calculus, but a specification language to describe behavior of concurrent systems. Not only just describe the behavior, but also do some kind of analysis using some notions of behavior equivalences. Now, they have their own calculus, but to give the semantics, or rather to give that operational semantics, uh, it was quite apparent that it became quite clear that labeled transition systems, which are very similar to non-deterministic automata, are sufficient for this purpose. So more formally, an LTS is a triple, um, which consists of X being the set of states, A being the set of actions, and the third component is a ternary relation called the transition relation, which tells basically how we go from one state to another state under which action. So the missing ingredients with respect to a non-deterministic automaton is the notion of acceptance, the set of accepting states. And the idea here was that since I think this has not got anything to do with concurrency, but rather the systems which they were interested were more reactive of nature. So the things which are running forever, for example. So in contrast, automaton or automata-like devices are recognizers of languages, but here there was no recognition as such. These were the models of reactive machines, so to speak. So to give you an example of a transition system, so on the left, I have a very simple transition system of a very simple vending machine. It starts from a state X, and then a user puts in a coin, and then the user gives a choice of selects either coffee or tea, and then the respective beverages are served, and the machine basically the behavior terminates there. So apart from these specifications of systems as transition system, they were also interested in when are two states equivalent or behaviorally equivalent. And the notions they were studied in this paper was something called bisimilarity. And this bisimilarity, to describe this, I need to say what a bisimulation relation is. So a bisimulation relation or R is a bisimulation relation, R being a binary relation on a set of states X, if and only if it satisfies two properties. The two properties are basically telling they are saying certain transitions from left to right may be simulated, and the second one says the transitions from right to left must be simulated. So a bit more formally, the first one, first being this one, says whenever two states, let's say X and Y, are in the relation R, and X can do an A step to some X prime, then Y must be able to mimic this A step, and the targets must be again in the relation. And likewise, the second one is symmetric to the first with the role of X and Y interchange. So it says if whenever X and Y are in the relation and Y can do an A step, then X can also mimic this A steps in such a way that the targets are back in the relation. So this was the definition of a bisimulation, but it turns out that the bisimilarity which they were really capturing was something, the union of all bisimulation relation. It has a fixed point flavor to it. We will see that later in this presentation. So intuitively, two states, X and Y, are said to be bisimilar if and only if there is some bisimulation relation which relates which relates the two states, basically. That's the point. So if you look at bisimilarity at its work, suppose we now consider the two transition system with X, which I have already described in them, and the let's say another one. This one, the first one is called spec, and this right one is called, let's say, the implementation, which starts from Y, and it is non-deterministic in nature. And the question is whether X and Y are bisimilar. So any insight, any answers? Do you say consider X and Y are bisimilar, or they are different?
Different.
Yes, they are different, because on the right in the implementation, the problem is once we take the coin, the machine takes the choice of offering a beverage, coffee or tea, and this could be made more formal by saying, for example, if we relate X and Y, then coin must be related. So X1 must be related to both Y1, because we want to satisfy uh, one of the two, let's say the transfer property from left to right, or we can also relate to Y2. But the problem is that this intermediate state can neither be related to Y1 nor to Y2. And the reason being, if we relate, then X1 can do a T which Y1 can't do, whereas Y2 can't do a coffee which X1 can do. So in this case, X and Y are not bisimilar. And intuitively, the point of bisimilarity was to say, when can you fuse non-deterministic branches into a deterministic one? So that's what it tries to encode in these two transfer properties. Now, if this definition of bisimilarity or this behavior equivalence is an intrinsic one. It's intrinsic because it is defined as a relations on the states of a transition system. Whereas what we would like to know or formulate is an intentional definition of bisimilarity um, where we can check whether two states are bisimilar by doing some experiments on the respective two states. And the way to do this is via logic, which is called Hennessy-Milner logic, and its grammar or the syntax is given by, you take the operators or the syntax of propositional logic, so you have true, the negation, conjunction, and you add something called diamond modality, one for each action. The point of diamond modality, or the semantics of a diamond, so a state satisfies diamond modality, diamond A phi, if and only if the state can do an A step, and more importantly, the target state can satisfy the formula. And because the logic has negation, there is a dual operator to this diamond modality called box modality, written by this box A phi, which can be, so if diamond is may modality, then the box is must modality. So X state satisfy box A phi whenever every A successor must, all the A successor must satisfy the formula phi. So we have now two formulation. One is an extensional and another was an intentional. And the obvious question is whether these two notions of the same behavior equivalence as conformance notions, is whether they coincide or not. And this was first proven by Hennessy-Milner in 1980. And the requirement, what they need is that the transition system should be image finite. So it's the image finiteness just means that for each state, the set of A successor for every action A must be finite. If you have this image finite restriction, then bisimilarity coincides with logical equivalence. So in the proof, this image finite restriction is only needed when you want to prove the implication from right to left, whereas the implication from left to right is always true. Okay, so any questions so far, or should I continue? Okay. So this was the main theorem which was shown by Hennessy-Milner, and this it was refined further by Rob van Glabek in 1990, where two arbitrary. So if you notice, there was this restriction in the previous theorem, that the restriction was that the transition system should be image finite, and he generalized this result to an arbitrary LTS, but his idea was to include arbitrary conjunctions in the logic. His main result was not only this, but during the period, let's say between the whole of 80s to 1990, there was some computer scientists formulated various notion of behavior equivalence. And he also gave this spectrum, which is a lattice of equivalence relation, where a bisimulation relations sits at the very top. And these arrows are actually telling that, so if bisimulation is, if there's, so the arrow between bisimulation to two-nested means that its bisimulation is finer than two-nested simulation. And what he showed in his 1990 paper was that he not only proved this theorem to bisimilarity, but to all other notion of behavior equivalences. Around 2000, the focus shifted from equivalences to bisimulation metric, because we wanted our notion of behavior equivalences to be robust with small changes. For example, especially when your model of systems involves quantities like probabilities. So in the context of probabilistic transition system, those who are unaware of this, but they can be viewed as labeled Markov chains. For this particular model, Van Bruegel and James Worrell first generalized this notion of bisimilarity to bisimulation metric, and they prove a similar result or they prove Hennessy-Milner like theorem for bisimulation metric. Towards the 2010 to 2015, a student of Kim Larson actually started working on something called a quantitative linear time branching time spectrum. So this spectrum is actually in the literature called linear time branching time spectrum. Anything below this curve is linear time, and everything above is branching time spectrum. These are because why they are called branching time is, if you look at their logic, they have some form of conjunction in their characterization, whereas the linear ones, the characterizing logic are free of conjunction. So so this student actually tried to generalize this semantics, or this lattice of equivalence relation to behavior pseudometrics, and this was quite recently finished or published by Uli Fahrenberg, or continued and finished by Uli Fahrenberg and Axel Liege in their paper called Quantitative Linear Time Branching Spectrum. But their work was restricted to to a transition system, a form of transition system called metric transition system, where the set of actions, the set A, carries a metric structure. Another missing or important observation is that in this particular paper, the logical characterizations were still missing. What they have shown is basically how the spectrum may look like, which behavior metric is below one another, but they haven't shown, or they didn't they didn't give the logical characterization of the corresponding behavior pseudometric. Okay, so now once we have done this, seen this picture of or this survey of Hennessy-Milner like theorems, now I'm going to try to generalize this to systems which are modeled as something called coalgebras. Now, around the same 2000 period, these coalgebras as a mathematical structure were rediscovered by Jan Retton, Bart Jacobs, and Adamic. And their idea was to, or their point was to say that various transition system or automata-like models in computer science can be abstracted or seen as under one mathematical or universal definition of coalgebras. And to describe this notion, I need a notion of a category, but and of course a functor on this category. But we are going to work as if our category, working category, is just sets. So, so we need So we need a category C, some working category, which would be our set, and we need a functor. So this functor is actually what they call modeling the branching type. It'll be apparent once we see these examples. Just this. Okay. So, but the idea of what is a functor, roughly, it is one can view it as a sort of two-sorted mapping. So it maps a set to another set, and it maps a function to another function while preserving the type. So if you have a function from x to y, then a functor will not only map will give you some function ff, which is whose type would be fx to fy, basically. So it's a sort of a two-sorted mapping. So then a coalgebra, if we are given this data, then a coalgebra is a tuple, x modeling the state space, which is an object in this category, and a coalgebra map, which is a map in this category given of the type x to fx. So here are some examples. So first we consider when f is given by what is in literature known as machine under functor. So for each object, so set f of x is nothing but the set, the Cartesian product of the function space x raised to a times the set of booleans, basically 0 and 1, which is indicated by 2. So an element of fx is a pair, let's say a function and a boolean, where f is a function of type a to x, and b is either 0 or 1. Basically, that's the. Now, if we look at the coalgebras, which are maps of this form, then they are nothing but deterministic automata. So there is something called category of coalgebras, but which I'm not going to say. But roughly, the idea is that F coalgebra for this particular endofunctor, for the machine endofunctor, corresponds to deterministic automaton, because for each state C of X, you will say for each action where I'm going to, you will have you have a pair. One will say what is the next state possible under an action A, and the Boolean will tell whether the state X is terminating or not. Yeah? So if it is terminating, then you will have a 1. If it is not, then you will have a 0 there. Another example is we stick to sets, but this time we take F to be the power set functor. And so for each object, F of X is basically the power set of X, all the subsets of X. And this time, when we look at the coalgebras, they corresponds to what are known as unlabeled transition systems, or if you are coming from the world of logic, they are cryptic structures without any notions of atomic propositions. Let's do something a bit more interesting. So, for example, if we take F to be the distribution functor, then the F coalgebras are in one-to-one correspondence to what we know as Markov chains. But now let me say what a distribution functor is. So distribution of X is now going to be the set of these mu functions from X to the interval 0, 1, which has the property that mu has finite support. And on objects, so remember I said a functor tells it's a two-sorted thing. It not only says what happens to the set, but it also says what happens to the function. And in this, we are saying df takes a distribution over X, and df of mu is now a distribution over Y, which is evaluated at some Y as you take all the pre-images of Y under F, and then you sum it up. And they would be finite because mu is of finite support, so therefore the sum is defined. And so if you look at the coalgebras of this kind, they are special. One can view them as automata-like structures where, for example, the outgoing probability from each state sum up to 1. So I must also say that the sum of all the I must also add the restriction that the sum of all X which are which has non-zero support must add to 1. So in this way, then we enforce the restriction that the outgoing transition, the probability of outgoing transitions, when you sum them up, is actually 1. So a coalgebra is nothing but can be viewed as a generalized automata or transition system. Now, so the point of this talk is to establish this work is to establish this Hennessy-Milner theorem for structures like this for coalgebras. So we have said what coalgebra, how we are going to model the systems. Basically, if we go at this part, these are models as coalgebras. But we have to say now how the conformance, the notion of conformance, are going to be modeled or encoded. So the notion of conformance could be either an equivalence relation or it could be a pseudometric or a distance function, as in pseudometric over a set X. Okay, so before I try to formulate this, um, I'm going to motivate why I can model conformances as index category. And to do so, we're going to do step by step. First, we are going to look into two sets. Um, One is the EQ of X, which is the set of all equivalence relations on a set X. And another one is the set of all pseudometric or distance functions of the type, so x times x to the closed interval 0, 1, which satisfy all the properties of a metric space except one, namely if the distance of 2 points is equal to 0, then it may not be the case that the 2 points are the same. So if we look at these two sets, over some set X, then one thing we notice immediately is that these two sets are ordered structures. Equivalences can be ordered by subset relation, and so equivalences could be ordered by subset relations, and our pseudometric space, I'm going to order in a by the opposite order, and the reason being because when you look at the metric spaces, or when you look rather at this closed interval 0, 1 in the context of metric space, 0 is considered as absolute truth and 1 as absolute false, and everything below is degree of trueness of falsity, as you see. So so 0 is my top element, and 1 is the least element, basically. Um, Apart from being these two structures having an ordered uh, presence, they also contains arbitrary meets. So, for example, in the case of equivalences, the meet is given by um, intersection, whereas in the case of pseudometrics, the meet is just given by taking, because we have flipped the order, is given by just taking supremas, pointwise supremas. Yeah. Okay. Now, so the observation is the conformance notions are ordered and they contain or arbitrary meet exist. Uh, the second is about reindexing or pullback operation. So suppose we're now first considering equivalence relations. Suppose we have a map, a function from x to y between two sets, x and y, and further suppose we are given a relation R on an equivalence, so R as an equivalence relation on y. Then we can always create, or we can pull back this relation, which is denoted by this f star R, which is now a new equivalence relation on X. And this star or reindexing operation is given by 2 points are related, X and X prime are related in this pullback relation if their image are already related in the original relation. This operation preserves equivalences, so this star operation is a valid operation over this meet semilattice. Similarly, when we look at the case of pseudometric spaces, if we have a function from x to y and we have a pseudometric on y, then we can always create pull back this distance to create a new distance on x, which is again denoted by f star d. And how is this defined? Well, if we have a function from x to y, then by tupling we can write as a function from x times x to y times y, where we on where f times f basically takes a tuple and apply independently on the two components, and finally you compose that with the given distance, you get the new distance on x. So a distance, the pullback distance on some points x and x prime, is nothing but the distance of the image of fx and fx prime. Yeah. Now, the final property which the structure preserve is that these pullback operations preserves arbitrary means. So if I pull back, so in the case of I guess in the case of equivalence, it's quite easy to see, because the inverse function, which is the real definition of the pullback operation here, it is preserved under arbitrary intersection. Likewise, one can also show that this fact is also true for pseudometric spaces. So if we have these properties, one can quickly say that a conformance is nothing but, or conformance is modeled by an index category having index limits. In more simpler terms, it just means for each object, for each set, phi of x is now a meet semi-lattice, and the star operation for each function preserves these meets. So so we are going to model systems as coalgebras, conformances, which can be equivalences or pseudometrics, as thin index categories. So they are thin because for each x, phi of x is a poset. It's not a full-fledged category. Okay. Now, but
so just one question. So what is POS for you?
POS would be the category of partially ordered sets. So the objects are posets and
order preserving functions.
Yeah, right.
Okay. Yeah.
Okay. Any other questions? Okay. Okay. So yeah. So if we now go back to our Hennessy-Milner characterization, you notice that the logic induces an equivalence relations. And the reason is, well, each formulas actually can be viewed as a function from some or can be viewed as predicate over state space. And in the classical setting, the truth there is an since we are considering Boolean valued predicate, the truth values is basically two valued set. So to generalize, now we are making a step from conformances, and we are first going to establish what is the relationship between predicates and conformance. And to do so, I need two more assumptions, and then I can prove one theorem. So the first one is just there because for foundational reason. So my category is locally small. So this just means that for each for any two pair of sets, x and y, the maps between x and y forms this collection of maps between x and y forms a set, basically. Okay, good. Well, set is locally small. The third is rather more interesting one, which is interesting from the application. There is a truth value object omega living in our category, and a conformance living on top of this truth value object. Now we will. I'm going to instantiate this in a moment, but the main result is once we have these. Once we have these three assumptions, under these three assumptions, I can relate the world of predicates and the world of conformance by this Galois connections. So on one hand, on the left-hand side, this is the world of predicates. It's the lattice of all. It's a Boolean lattice, so it's a Boolean algebra. So it is a subset of all predicates, and here predicates are modeled as maps from X to some truth value object omega.
But I think that the notation is really not defined. So what is this Cx omega, and what is this P over it?
Okay, so Cx omega is the collection of maps, or a set of maps between X and omega. And P,
X is just an arbitrary set.
And X is in an arbitrary object in our category.
So basically as an instance of that, you would see a predicate as a Boolean valued function.
Yeah.
So that would be omega would just be the Booleans. That would be, and you generalize it in basically admitting more general truth objects, right? That's
correct.
The thing.
That's the idea.
Yes,
yeah.
and then you take basically the set of all such functions, which is the set of all predicates.
Yeah, exactly. Okay. Yeah, we will come back to the examples in a moment. So now, yeah. So I was saying that there are two worlds. One is the world of predicates, and another there's a world of conformance. First, let me say what the right adjoint gamma does. So what essentially, morally, the right adjoint does is that it takes a conformance D and it produces a set of predicates which are, I have not said defined non-expansive, but you will see that it will come out to be non-expansive. Or let's put it like this, that these predicates...
Harsh, again, I cannot understand it. I'm confused because you said that the conformance is something of type phi applied to omega. Yeah? But so, and I assume such a D lives basically in this kind of phi applied to the truth object, but now you have this kind of phi X up.
Yeah.
And so what is that? So if I apply phi X has basically the type poset, right? And you...
Yeah.
And then you take the opposite of a poset, but the opposite of a poset is again a poset.
Correct.
But why is that a conformance? I thought conformance are phi applied to truth.
Okay.
I mean, the types do not fit together, right?
No. Okay, so it fine.
It doesn't fit together because your phi is from C up into pos, but now your omega lives in C. So shouldn't it be in this definition D of omega in phi blah? Shouldn't it be something like omega? No, I do not know. I mean, I find it confusing.
Okay, so let me try to...
because phi is a functor, so that's basically just the object part of it.
Exactly.
That's why it works. Okay, I see now.
Okay, and another reason what I'm saying is that what I said it incorrectly is that this whole world should not be actually seen as the conformance. The conformances are elements of phi X. But what this Galois connection is telling is that the world of predicates and the world of conformance is arranged in some contravariant manner. Okay.
But that is a meaningless statement if we don't know what these notions mean.
Exactly. We will see. We will instantiate these notions in the next slide. But let me just give you what alpha X and what the left adjoint and the right adjoint looks like in this. Give you just a formula. And then we'll instantiate this formula and see what it means in the concrete cases. Okay, so the first bit, the right adjoint, it takes a conformance D, which is an element of phi x, and it produces those predicates which are non-expansive with respect to uh, this conformance, basically, or they are respecting this conformance. We will see what this inequality means in the concrete cases. Now, the left adjoint, what it does, it takes a set of predicates and it produces the conformance alpha x of s in such a way that all the maps in S are somehow again non-expansive with respect to alpha x of s. And the concrete formula is given by this expression, where if you have a d omega, as you notice, so you have a p which is a map from x to omega, and d omega lives on top of as a conformance over omega. So p star gives you now a conformance living over x, and now because there are more than one, we just take the meet, because meets are defined or meets exist, and we just take the meet of all such p's, and this gives basically a conformance living in over x, basically. Okay, now I mean this is quite abstract. Let's try to instantiate these two things on a very basic setting, namely when C is set, the and omega is the booleans, the set containing 0 and 1. The conformance over true over omega is nothing but equality on 0, 1. So 0 is equal to 0 and 1 is equals to 1. That is what this equality is saying. Then based on this previous theorem, we have a Galois connection between the space of Boolean predicates and contravariantly related with equivalences on the other hand side. It is also well known that the function space from x to 2 can also be seen as power set of x. So we can actually there is basically an isomorphism between the two lattices. So you can have this particular lattice can also be seen as power set of x. In category theory, we usually distinguish the two power set. One is a covariant one, and the set of function space from x to 2 is considered the covariant one. But if we don't want to, for simplicity, for now we just view them as the same power set. Okay, so how does the two adjoint situation looks like, or the two adjoint looks like? First, the right adjoint. So we have a relation R, which is an equivalence relation on X. We apply the right adjoint. We should produce now a set of sets over X, a set of subsets of X. Okay, so we collect those subsets U of X such that U is R closed. In a sense, every point which is in U and any other equivalent point with respect to the relation R must be also in the U. Yeah, so that gives you the right adjoint. The left adjoint is given a set of such subsets, which I indicate by bold U. Then I must produce a relation which is an equivalence relation on X. And the way it is done is X and X prime are in this relation if and only if for each there's no if and only if these 2 points are indistinguishable from every predicate in this bold U. Or more simply, for each U, if X is in U, if and only if the other point X prime is also in the U. So another way of saying alpha X of U is the smallest equivalence such that every predicate U in bold U is R closed. Yeah, so this is one example. Let me quickly do one more quantitative example. So this time we are going to take the truth value object to be the closed interval 0, 1. And now our parameter, or the conformance over closed interval 0, 1, is going to be, I think this is called Euclidean distance. So the absolute absolute value of the difference between R and R prime, where R and R prime are elements in this interval. Okay, now.
Sorry, what is the type of R and R prime? Where do they live?
So R and R prime are elements in the interval 0, 1. Okay. So now we instantiate the framework, and what we notice is on the left-hand side, we have the subset of all fuzzy valued predicates. So fuzzy valued in the sense the predicate is a more a function from X to the interval 0, 1, closed interval 0, 1. And on the right-hand side, our conformances are pseudometric spaces, which are ordered dually or up in the opposite order. And now we have another op coming from that junction. So the right-hand side can be further simplified as to just the usual lattice of pseudometric spaces on X. Now, if I apply the definition of gamma, so for each pseudometric on X, gamma X of D will give us those predicates that are, so P are those functions from X to 0, closed interval 0, 1, such that these functions P are non-expansive with respect to the distance D. Yeah. And the left adjoint is given in a similar fashion as, or can be stated in a similar fashion as in equivalence, that for each set of fuzzy valued predicates, alpha X of S is the largest distance such that every function P which are present in S becomes non-expansive with respect to this distance. And more concretely, it's given by this formula. I'm not going to say what happens when it is when it's the case of joint semi-lattice, but I want to just close this at the place where I can say where we exactly are.
Just a question, another question. Instead of pseudometric spaces, could you also have metric spaces on the other side?
Yes, we can. So the only restriction is as long as you have any complete semi-lattice, it will do. So the two requirements are basically these two, that phi X has to have arbitrary meets. So internally, in turn, it becomes a complete lattice, and the reindexing must preserve these meets.
So, but that's basically just the general condition that you have on adjunctions, right? So
not necessarily. So these are the conditions on the index category phi.
Okay, one question. So
Yeah.
You said you must have arbitrary meets where. I mean, I can take like a bunch of metric spaces that have a meet like 0 distance. Wouldn't that be a problem? Like you take the meet of a metric and then you scale it down by epsilon and over all epsilon greater than 0, and you take the meet of all that. Would that be a problem?
No, because in the case of metric spaces, our order is flipped. Remember, so the meat becomes suprema.
Okay, sorry, I missed that.
Yeah, so that is not a problem. Okay. Now we have 2 minutes and to say what a Kantorowicz lifting is. Instead of that, I'm going to explain, maybe end this talk of how this adjunction could be useful in improving this Galois connection in this Hennessy-Milner theorem. So we go back to the basics. So we have in this adjunction now every with whenever one defines a logic, semantically defining a logic means just defining of transformations between predicates. So that means one is just technically just defining something called what we call logic function, which tells how to map a set of predicates to form another set of predicates. Yeah. Now, since it's an Galois connection, one for each x, we can repeat this, and we end up in the similar situation. Now, the behavior conformance, which are most of the time defined in the literature, they can be defined as this composition of gamma, logical function, and alpha x. And this is what we call behavior function. It turns out that all the conformances in the literatures are nothing but the fixed point of such a behavior function. Moreover, under certain restrictions, one can also show that the least fixed point of the log function, which one should view this as the set of modal formula, which is generated by, for example, a syntax. If I apply alpha x, then this corresponds exactly to the greatest fixed point of behavior function. And this exactly is what Hennessy-Milner theorem is. Because on the left, you have the set of modal formula generating the conformance using the left adjoint, and you are comparing that notion with respect to the notion of or the conformance generated by the greatest fixed point of this operator. And this works out because the left adjoint preserves the co-limits, and the least fixed point operator is always defined using co-limits. So the alpha of some co-limit expression will be again a colimit expression, but colimits in the opposite poset becomes nothing but greatest fixed points. So that's why such a result works. But this is not true in general. You have to enforce some conditions, then this result becomes valid. But yeah, I guess that is for some other time. But since time is up, I would like to stop at this stage.
I guess because Max is not there, are there any questions? Well, no, first of all, thank you very much for the talk, Harsh. And now, are there any questions? Yes, everybody applauds.
Yes, sorry, could you repeat the definition of this log thing?
Okay. So usually the log thing would be coming from some syntax. So for example, in the Hennessy-Milner case, you have this syntax coming from this one. Yeah. So the log in this particular case would be nothing but take a set of predicates. So you should basically, the one which we used is take let me explain. So the log operator in for this particular setting would be defined as take the diamond modality, apply it on some formula which is described as Boolean closure, which can be rewritten as Boolean closure from functions from S. Yeah. So one can view this as a formula of this kind, for example. So every such syntax induces something called a logic function, which essentially tells you how to map a set of predicates into another set of predicates, basically. So it's hard to give a concrete definition. It depends on the concrete case study, basically, on what kind of system we are working on.
Okay, thank you.
So this mu and nu, they are least and greatest fixed points, right?
Yes.
So is this an instance of Lambek's theorem?
No, it is an instance of the theorem which says left adjoint preserves colimits. It's that, because mu of
but I think that's essentially what it is. Yes. But you have limits and colimits at the same time, right?
Yes. Yeah.
You have colimits on the left and limits on the right.
You have actually technically we have both limits and co-limits on both sides. It's just
no,
that
but I mean, but in the formula, so there's a co-limit on the.
Yeah.
There's a co-limit on the left and a limit on the right. This new on the behavior.
Yeah, is a co-limit.
That's a co-limit, and the mu is also a co-limit.
Nu becomes the co-limit. Yes.
So both mu and nu are co-limits.
So
It's not one limit and one a co-limit.
So the mu operation is nothing but given by this by such a thing. Okay. So this is actually
That's a co-limit.
That is a co-limit. Okay.
Yeah.
And alpha of such a thing would transform this into because it's contravariant, so it will flip it around.
Yeah.
And now it becomes a limit, basically.
Yes,
so
exactly. Okay, thanks. Yeah.
So the right hand side is a limit.
Yeah. Okay. Thanks. That's fine. So it looks indeed like Lambek's theorem a bit. Thank you.
Okay.
I also have a question. It's been some time, but I think when I learned about Coalgebras, there was some theorem that said something along the lines of if your functor preserves weak pullbacks, then bisimulation and modal equivalence become the same thing, which is also in this sort of line. Is there some comment that you can make about that?
Yes, but I haven't said something called how do I capture bisimulation in a general sense. So what would be the smallest? So yes, we can say that there are two ways. Okay, so if we are working just plainly on two-valued conformances, then as you said, there are one can define a notion of equivalences by coalgebra homomorphism, which is called behavior equivalences. And the other one is using by the bisimulation relation originally from Hennessy-Milner style. Now, usually in our framework, we can model, we can encode such a notion of behavior equivalences. And so basically what you just stated is saying that for weak pullback preserving functions, these two notions are the same, but I think this we can't say directly from our framework, because as far as I'm aware, we are mostly encoding such a formulation, not this one. So we don't have right now a characterization or a characterization of this results, basically.
All right, thank you.
Yeah.
Are there any other questions? Otherwise, let's thank again Harsh for his really nice presentation. Thank you so much, even with COVID.
Thank you.
Okay, bye-bye.
Bye.
Bye.
Bye.